An event tree is a standard or a common risk assessment tools that we use to evaluate or to look at the possibility of an failure rate. So event trees normally begins with an initiating event, and then we work towards a final result. And this approach is sort of like inductive. The methods provide information on how a failure can occur and the probability of the occurrence. So the typical steps are generally like you identify what initiates the event, and then we identify the safety functions that design to deal with this event. And then we construct the event tree and we look at the results of this. And the next thing is we describe the resulting accidents events sequences. So if the appropriate data are available, this procedure is used to assign numerical values to the various events. This is very effective to determine the probability of certain sequence of events and decides what improvements are required, which you can see in the next example. Okay, let's take a look at this example here. We have a high temperature alarm. This is actually the same examples that we used for our HAZOP analysis in the previous slides. In the previous classes. So a high temperature alarm has been installed to warn the operator of a high temperatures within the reactor. So here we have an alarm system. Okay, so for high temperature. And so now we want to construct an event tree of a loss of events with this Coulomb initiating event. So let's take a look at what we have. So loss of cooling occurs once a year, and the hardware safety functions fail 1% of the time, meaning 0.01 failure per demand. And if let's say when it fails, our operators are so observant that they actually can notice high reactor temperatures 3 out of 4 times, means 75% of the time. And out of these 3 or 4 times, they manage to re-establish the coolant, means they can restart. This is what we call the restart. And of course, then operators successfully shut down the reactor 9 out of 10 times. Okay, so we want to construct an event tree from this system. So first we want to talk about the event failure. And we talk about the failure. Okay, so from the earliest one, we have high temperature alarm. Okay, so we have this high temperature alarm here. So part A will be high temperature alarm. Okay, it fails 1% of the time. And if it's failed, then we have operator observe high temperature. And this one, we say that it occurs in notice 3 out of 4 times, means 75% they notice, and the failures will be 25%. Okay, so once they notice already, what they do is they restart the system. Again, 3 out of 4 times means 75% success rate, restart the system. So here we say restart, and it's again the failure rate is 25%. But in the event, if we can restart, means everything's go back to normal, it continue operations. But if cannot restart, then operators will have to shut down the reactor. So shutdown is 90% of the time. Okay, so shutdown, if they want to do shutdown, means 90% of the time it will be successful. So it will be 10% failure. So if you are to construct this event tree and fault tree, so this is what I'm going to write. Okay, so this failure is 1 per year. Okay, so failure 1 per year. This is what we call the loss of cooling. Okay, so These high temperature alarms will tell us 99% of the time, so 0.99 it will be successful, and 1% of the time it will fail. But out of this 1% of the time, our operators will be able to notice it 75% of the time here, and 25% of the time they will know anything. So what happens if at this 25% of time, if they don't know anything, this will definitely be a runaway sessions already, meaning things might just happen. So if we have high temperature alarm, we don't need our operator interventions here. So now the operators need to take actions. They will have to restart the system. So again, 75% of the time it gets to restart. And when it restarts, all good. So operations normal. Okay. So 25% of the time it cannot restart. Again, same here. If they get to restart, this is operations normal, as normal. And 25% it didn't get to restart. So if when it doesn't get to restart, so what they do is they shut down the system. Okay, so 90% of the time it get to shut down. So okay, at least we have a shutdown. But 10% of the time it failed to shut down, the next thing is emergency evacuations. Okay, let me go back to the earlier slide. So then we have a runaway. Okay, same thing here. 90% of the time you get to shut down. And 10% of the time you have a runaway scenario. Okay, so if we want to calculate what is the failure of these situations, okay, so now we have this failure here. Oops, we have this failure here over here 1 times, second and third. Okay, so what we do is we times all this data. So the first failure here is 1 times 0.99 times, so this one, this one, this one, and this one, 0.25 times 0.10 is our first failure. Okay, you get the number. Our second failure is this route. Here comes this one, come this one, and come down this one, and this one is our second route. So the second failure is again 1 per year times 0.01 times 0.75 times 0.25 times 0.10 is our second runaway scenario. Our third runaway is again here to here, but this time to here, and immediately it goes runaway. Okay, so the third one will be 1 times 0.01 times 0.25, and immediately it runs away. So you have 3 data here, X, Y, and Z. So your total failure would be X plus Y plus Z. And you get your total sequence. So it comes out, if let's say you use your calculator to calculate, it comes out roughly about 0.025 failure per year. And if we are to convert to how many failures how many years for one fail. So just have to do 1 divided by 0.025. You get around 40 years. Meaning, every 40 years, we are expecting a runaway system, which is actually very, very dangerous. Yeah, so this resolve this example here. As you can see, the failure rate is as what we calculated out, 25% or 0.025 failure per year, which converted to 40 years is actually extremely high. So what we suggest now is, let's go back to the earlier slides, we add in, we add in a shutdown system, high temperature shutdown system. So meaning if everything fails, at least we have this shutdown system to help us to reduce this occurrence. So now let's take a look at, again, because we are looking at hardware functions, safety functions fail 1% of the time. Okay, so this is 99% of the time it works. So this will work for two things now. One is the high temperature alarm. Another ones will be the high temperature, what's that called? Shutdown system. Okay. So instead of having just D here, we have an E now. Okay, so again, the events is still the same. Loss of cooling. And it happens, failure here is still once per year. Okay, so the first events will be high temperature alarm. As same, again, the failure rate is 1%. And in the events, if let's say when we have this one, so what kick in next is the automatic shutdown system. So high temperature shutdown. Again, this is another 1%. Then we have, if all these fail, we still have our operator notice high temperature. So this was, as early mentioned, is 3 out of 4 times, so failure rate is 25%. And now, because after the auto shutdown, now we do the manual restart. So restart system fails also 25% of the time, and E is operator shutdown. So these are manual. So automatics will come first, these two automatic, and then the rest is manual system. So this one failed 10% of the time. So again, let's create our event tree. So here we have 1 per year. And high temperature alarms, it will rang no matter what. So we have 99% of the time it rang, and also 0.01% it doesn't rang. But regardless whether it rang or not, because now we have a second system in here. So this system will say, as long as it detects high temperature alarm, and these two are not linked, yeah. So once it detects, it automatically shut down, but there's 1% that it is not shut down. Okay, so once it's shut down, this is done. This is safe. Okay, so again, 0.99, 0.01, so this again is safe. So now, without alarm, without this one, we still have our operator as our next check gate. So operator notice it 25% of the 75% of the time, and fail to notice at 25% of the time. So if this one doesn't work, the shutdown doesn't work, the alarm doesn't work, operator didn't find it, it's gone. This is a runaway, the first runaway system. Okay, so now we have operators working here. So of course that operator will try to restart the system. Yeah, because both sides, this one operator notice, this one operator being informed by the alarm. So restart, we get to restart 75% of the time. Fail to restart 25% of the time. So this one we get, this is again safe. Yeah, so here 75% of the time this is safe. And 25% of the time they fail to do that. But we still have one last check gate, which is the red color emergency shutdown button, the manual shutdown button, and this works 90% of the time. So again, this is a safe system, but this 10% will be a runaway system. Okay, again here 0.90 here is safe, and 0.10 here, this is a runaway system. So if we are to look at the system now, okay, so we have runaway system here, we have runaway system here, and we have runaway system here. So let's put up the first route. First route will be here, come to this, and this. That's the first route. Okay, put a different color for second route. Green, this one, here, here, and here. This come to the second runaway. And of course the third route. Again here, comes here, 0.01, and the 0.25, and the third runaway. So if we are to calculate each one of it, the failure. So again, first failure, we have 1 times 0.99 times 0.01 times 0.25 times 0.10. Okay, your new x1. And the second failure is where you have 1 times 0.01 times 0.01 times 0.75 times 0.25 times 0.10. Here you have your y2. Just now that's x2, sorry. So your third failure that is being shown here is 1 times 0.01 times 0.01 times 0.25 is your z2. So currently your failure rate per year is x2 plus y2 plus z2. And this, you may start to calculate again. So with this 0.01 additional in place, you will notice it goes to something like 0.00025 failure per year. And if we convert it to how frequently it breaks down in terms of year, you get 1 over 0.00025. This gives you a number of 4,000 years per failure. You can see that just by adding in one shutdown system, we increase that chances of not failure. So meaning we reduce the chances of failure from the original 40 years to right now 4,000 years. So you can see how big that difference is just by adding in one more check gate in here. Okay, that explains why we do inventory and how we use inventory to calculate the risk of the system. after we have talked about event tree analysis, the other trees that we often use for safety analysis or risk assessment is what we call fault tree. Fault tree started in the aerospace industry, and it has been extensively used by the nuclear power industry to qualify and to quantify the hazards and risks. So it is slightly different from event tree. And so it's normally started with a well-defined accident, or what we call a top event. And then it worked backwards to the various scenarios to work towards the root cause. So the events in the fault trees are not restricted to hardware failure. It also includes software, humans, and environmental factors. However, we often stop the fault tree analysis at places where that is out of our control. Let me show you with this example. Okay, so we start with a simple one, a flat tire. Okay, so a flat tire as a top event. Okay, so we have a flat, and then we start to brainstorm what can cause flat tire. So they come up with two possibilities. One is the tire failure itself. The other one is the road debris. And remember, I mentioned that we stop at things that we cannot control. So can you control this? Controllable? No, because unless you want to, like before you go out and you want to sweep the floor all the way to where you want to go, which is not possible. So this is some things that we cannot control. Okay, that is why we stop here. So this is where we stop. The moment we find that no, this is not controllable, it's out of our control. Okay, so then we focus on something that is within our control. So okay, we have a tire failure here. So what can cause a tire to fail? So it can be, one is a defective tire, number one. The second is a worn tire, means an old tire. Okay, so if you are the user, you will stop here, okay, at the defective tire or worn tire, because both will require you to change your tire or repair your tire. If it's worn, then you want to repair it. If it's defective, then you want to repair it too. You want to change it too. So, but if you are a tire manufacturer, or you are a car manufacturer, that you get this tire into your shop, and the moment you put it up and you realize, hey, this is a defective tire. Okay, if you are car manufacturers, you would just tell your supplier, change that. But as a process engineer in a tire manufacturer like Continental, like Michelin's, then the defective tire is something that is still within your control. So you don't stop here. You stop here if you are consumer. But if you are the maker, you continue from here. Okay, so now you have a check gate, an all check gate. What can cause your defective tire? Okay, so is it too much material, recycled material, for example? Okay, and then it can be just a QA failure. So meaning there is an uneven here and there. So QA failure, if you are processed, then you stop here because this is beyond your control. This is where you want to feedback to your QA department and say, hey, look, take a look at this. You ship a defective tire to our customer, so do something. And so, but if you look back at what you can control, what is within your own control, you look at maybe your mold is already defective, or maybe it is something else that causes all these defects. So you can put a few more here, another one, and you continue. You stop at where you realize things that is out of your control. And then you take action for these places. Yeah, actions are required once you stop. Like for example here, this is not something that you can control, that's where you stop. So worn tire, your action is change tire. Okay, or perhaps you may want to look at how frequent you change tire, how frequent you do PM. So for your tires, do rotations, do balancings and all that to reduce or to expand the lifetime of the tire. And then for defective tires, do you want to claim warranty? Or do you want to change to another brand? So again, the moment you stop, this is where you can, I shouldn't use that square box because it means an event. So this is where you can take action. Okay, for even here is you can't control the road debris, but if you know that the particular road has lots of debris, maybe perhaps you look for alternative route. Yeah, so you take actions at where you can control within your own control. You can't take actions for things that you cannot control. Okay, so this is how we look at event tree, fault tree. And fault tree can be expanded a lot. This can go on and can go on and can go on until you find somewhere that you feel like, hey, I want to take actions over there. That's where you stop, and then you reassess what sort of actions you want to take over there. This gives us a good idea of like an accident, what could go wrong in an accident. It allows us to, this is a brainstorming sessions where it allows us to look at how you want your people to what sort of improvement CQI actions that you can take in your plan. So once we are looking at fault tree analysis, there are few steps that we have to look at, we have to follow. First is to define our events, our top events. What do you want to assess in this case? We have to be precise in selecting our top events, meaning when you have it overly precise, like we look at smaller things like leak in valve, leak in pump and all that, then you may realize you end up with a very small fault tree, or maybe it's just 1 or 2 layers. And if you start with an events that is non-precise, like fire or explosions, so many things can lead to this too. And you might realize that you end up with hundreds of pages of fault tree analysis, but you have not looked at what you really want. So a lot of time I will advise people to look at 1 layer deeper, like explosions of reactors. So what sort of explosion you're looking at? Is it caused by high temperature? Is that caused by static charge? Is that caused by whatsoever reason? So then we look at, if let's say we say, oh, it's caused by because of pressure too high, temperature too high, then that we take it as our top events, high reactor temperature. And also we want to define the existing events that those conditions are sure to be present, and also to define what is not allowed. Things like Mother Nature's, like tornadoes, lightning, earthquake, things like that would unlikely to be considered because we can't control it at all. Once we have all these definitions or boundaries, the next thing is we want to look at the physical bounds of the process, like what components you want to look at. Then we look at the equipment's configuration. So what valves are open, closed, what is a normal operating states, what are the liquid levels, and then we define the level of resolutions, meaning how deep do you want to go inside. So do you want to stop at, like for example, the valve, or do you want to go into the every small little components in the valve, like O-rings, like the bellows or something? And using a for tree, these are some of the symbols or the what we call the logic transfer components that you can use for tree analysis. So let's take a look at them. The one that we often use are the AND gate, the AND and OR. So you have an event, and sometimes the events, like for example, you need like fire. To start a fire, we need three things. You need oxygens, you need fuels, and you need ignition source. So in that case, you want to use an AND gate because you need all three to present to start the fire. Okay, but certain things that are like the earlier examples that we talk about, the flat tire, it can cause by root debris, or it can caused by the tire failure itself. So it's not to say you need both to have that events of flat tire, but either one can cause flat tire. In that case, you use an OR gate. Okay, the other ones that we normally use is the circles, which indicate the basic event. This one, rectangles, represents intermediate, and also then we end with another circles as the final event. Okay, so the rest we seldom use actually. So it's just mainly these four in our for tree analysis.